3.5 billion years ago, the Earth was in its second eon, called the Archean. Back then, it looked like a different planet. The atmosphere had way more hydrocarbons, which from space gave Earth a very pale orange haze. The oceans were rich in dissolved iron, so they were significantly darker and greener. Today, the surface area of land on Earth is 30%. The rest is obviously the ocean. However, 3.5 billion years ago, the Earth was even more of a water world, with estimates putting the surface area of land at less than 12%, and likely even as low as just 2%. So the total surface area of land back then was around 10 million kilometers square, similar to the surface area of just Europe. However, that land surface area was not congregated in a single spot like a continent. Rather, it was spread across in a patchy way across the ocean as volcanic islands that were propped up above the sea level by constant volcanic activity. The islands were also rather dark because that volcanic activity also constantly delivered plenty of fresh basalt. Mountain ranges and uplands on these islands were largely absent. Back then, the tectonics could not yet build and preserve a crust thick enough for the continents to form. That's why the surface area of land was so small, and also why most of the mountains which were present were entirely of volcanic origin, likely some 1 to 3 kilometers above the sea level. Today there is a pretty good example of that type of land that was present during the Archean. It is the Jan Mayen Island, located in the Arctic next to Greenland. It has a surface area of only about 377 kilometers square, but the volcano stands about 2.2 kilometers above the sea level. Its surface area is covered by glaciers in higher elevation areas, but also with greenery in lower elevation parts. However, large parts of the island also have dark exposed basaltic rock, which gives us an insight into how the islands of Earth looked like 3.5 billion years ago. Today there are quite a few other volcanic islands like Jan Mayen, but the number of these volcanic islands was drastically higher 3.5 billion years ago because volcanic activity was much more prevalent because the mantle was hotter. And the mantle was hotter because the Earth still had more leftover heat from the energetic formational period, and it also had more intense radioactive decay, which releases heat. The number of volcanic islands back then was probably at least many tens of times greater than now. Likely, there were more than 10,000 of them, potentially reaching a number greater than 100,000. Many of these were likely just a few tens of kilometers across, similar to Jan Mayen. But occasionally among those, there were likely some several hundreds of kilometers across, similar to Iceland, which is, at the moment, the largest island in the world made up from volcanic eruptions. Potentially due to greater volcanic activity, back then there could have been quite a few Iceland-like islands, along with some that are even a couple of times larger in terms of surface area. Quite a few of these volcanic islands were almost certainly in the polar regions, where for nearly half a year they experienced mostly sunlight, and for the other half, mostly darkness. However, even despite that, it looks like overall, the Earth's surface was far too hot to sustain large glaciers. Even the existence of small glaciers is uncertain. That is because some estimates say that the oceans had an average temperature of about 55 degrees Celsius, way above the current water surface temperature average of 15 degrees Celsius. That 55 degrees Celsius also reflects the temperature of the atmosphere near the sea level as well, meaning the land on volcanic islands was also extremely hot on average as well. However, polar volcanic islands with some really tall peaks still could have had times when it was snowing. Land cools down more quickly than water, and the elevation increase also decreases temperatures. This snow likely occurred during winter, which was likely similarly long to winter today. That is because the axial tilt of Earth was similar to the one today. The moon back then was significantly closer, which allowed for the axial tilt, and with that, the seasons to stabilize. The estimate is that the moon was on average about 300,000 kilometers away from Earth, quite a bit different from the current average of 380,000 kilometers. So it appeared to be visibly larger in the sky back then. Not only did the moon appear to be larger, but there is also a pretty good chance that it appeared to have a different color. That is because sometime between 3.8 and 3.5 billion years ago, the moon had a significant atmosphere. The rock samples brought back to Earth were studied, and the conclusion was that for about 70 million years, the moon had an atmosphere that probably had a pressure that was even somewhat greater than what Mars has currently. So, although thin relative to Earth's atmosphere, that is still potentially enough to produce a visual difference, especially because that atmosphere had quite a bit of sulfur. But the main component of that atmosphere was carbon dioxide. But what did the atmosphere of Earth look like back then? Well, as said, from space it probably had a pale orange haze, but from the surface, looking up at the sky probably revealed a somewhat different color. Likely it appeared to be somewhat white, and potentially a very desaturated blue. Because of the greater volcanic activity, that led to more volcanic aerosols in the atmosphere, which influenced the color of the sunset. At the same time, the sun was also noticeably less bright, so that could have also changed how sunsets appeared. Besides that, sunsets themselves were also more frequent. That is because a day on Earth lasted only 12 hours. So yes, on the equator, daytime and nighttime each lasted for just 6 hours. As far as what the atmospheric pressure was like, one study constrained the pressure as being between 1.1 bars, so slightly above the current pressure, down to possibly being as low as 0.5 bars. So about half the pressure currently present at sea level. If it was truly this low, that would allow for some pretty heavy temperature swings. But still, this study confirms that the overall atmospheric pressure on Earth 3.5 billion years ago was pretty similar to the one today. Besides the similar pressure back then and now, the Earth's atmosphere was also predominantly just nitrogen. There was, however, very little oxygen back then and a lot more greenhouse gases such as CO2 and methane. This is why the temperatures were so much greater despite the sun having a brightness level 25% lower. The lack of oxygen back then also didn't allow for the formation of the ozone layer, which then made it such that much more ultraviolet radiation reached the surface, which in turn made life on land and in shallow water certainly in this way harsher compared to today, but not enough to stop life from existing in those areas. For shallow water, it is very obvious that life existed in it during this time, but for land it is somewhat less certain. Still, it is likely that gram-positive bacteria evolved by this point. These are the types of bacteria that have a single inner membrane. However, they also have a very thick outer cell wall, which allows them to survive in dry environments such as land much better compared to gram-negative bacteria, which have two membranes, an inner and outer one, but a thinner cell wall. These gram-negative bacteria survive better in wet environments. So the surfaces of volcanic islands on Earth still potentially had these gram-positive bacteria that survive well in a dirt-poor, dry basalt areas. However, there likely wasn't anything much more complex than that, and likely no organism that would visibly coat the surface of dry land. So the islands weren't coated in any greenery. It was just dark basalt all across the islands, along with some probably very rare snow in high elevation areas. There was also obviously no dirt on those islands. This is still far too early for that. The amount of cloud cover over Earth during this eon is somewhat uncertain, but there were certainly clouds and likely a significant amount, significant enough for rain to be a common occurrence. With that, at least one mechanism for the formation of small freshwater lakes is plausible on volcanic islands. Likely those freshwater ponds and lakes also hosted freshwater bacteria that significantly differed from the ones found in the ocean. Now, the oceans back then were certainly not freshwater, but the question of how salty the oceans were during the Archean is still not entirely settled. Some studies suggest that they were significantly saltier through the fact that there were no continents for the evaporated salt to get trapped in, while another study suggests that the salt levels were similar, and it concludes that through the analysis of ancient rocks. So overall, it's hard to say. However, one thing that is pretty conclusive is the fact that the amount of dissolved iron in the oceans was much greater. So great, in fact, that it likely influenced the color of them, such that they look a bit green from space, and from the surface, the oceans would likely appear to be significantly darker compared to today. The reason so much iron was dissolved was because there was not enough oxygen to react with iron, which then allowed for iron to be in a dissolved state in the oceans. Otherwise, with oxygen present, the reactions would make the iron sink to the floor of the ocean. The ocean floor itself was also significantly different in that there was far less sediment, but at the same time, there were also way more hydrothermal vents because of the greater volcanic activity. Although hydrothermal vents do produce sediment, it's pretty localized and of a certain type. Today, the sediment is present globally on the floor of the oceans. 3.5 billion years ago, no such sediment cover existed. Primitive single-celled life likely thrived near these abundant hydrothermal vents at extreme depths, as they were a good source of nutrients, and the life forms there also likely differed quite a bit from the life present on land and in shallow waters. For shallow waters, there is some of the best evidence for ancient life 3.5 billion years ago. That is stromatolites. They are layered rocks, and the layers in those rocks formed by microorganisms that cement rocky materials and form microbial mats, and over time, as the mats build up, they produce layers. Stromatolites 3.5 billion years ago thrived in shallow ocean waters because there was no animal grazing because, well, there were no animals. Today they also exist in shallow ocean areas, but mainly they exist and thrive in super salty lakes where there are no animals to interfere with them. As far as the temperature of the ocean, the estimates for Earth 3.5 billion years ago range between 26 and 85 degrees Celsius. However, one study while examining rocks that were in a shallow area around that time suggests that the ocean temperatures were much lower than suggested by previous studies. So there isn't a single known number as to what the temperatures were like during that time. However, it is possible that there were just periods of several million years when it was unusually cold, but similar to today's temperatures. So that certainly allowed for not just snow but glaciers on volcanic islands. But besides those unusually cold intervals, the evidence points towards the idea that the oceans and the atmosphere was typically very warm during that period. Another notable difference is that 3.5 billion years ago, the ocean floor was very flat, at least much more so than today, since back then the tectonics could not yet build and preserve a crust thick enough for the continents to form. That also reflected on the ocean floor, which likely entirely lacked these extremely deep trenches such as the Mariana Trench. The trenches have these very obvious steep slopes that can stretch for thousands of kilometers. They form when two tectonic plates converge and the older plate gets pushed into the mantle, which causes for the seafloor to sink. However, 3.5 billion years ago, the plates just didn't work the way they do now, which didn't allow for the formation of trenches on such a scale. But there still could have been some small, somewhat unusually deep spots. However, although likely overall very flat, there is some evidence that the ocean floor still had some significant elevated plateaus. Pilbara Craton in Australia is where some of the oldest rocks on Earth were found. This is where some of the oldest evidence for life on Earth was found in the form of stromatolites in shallow water. This whole region likely existed as an uplifted part that stood out compared to the rest of the ocean floor, and this is likely due to the possibility that continental crusts existed at least as far back as 3.5 billion years ago. But still, the main dry land surface area of Earth during that time was most likely entirely volcanic. So that is what the Earth was like 3.5 billion years ago. It certainly isn't as complex as the planet is today, but it still had quite a few interesting things about it.